In this module, we're talking about combustion analysis, a technique for analyzing a compound to find its empirical formula. So this is a sketch of the apparatus that typically is used for combustion analysis. What you do is you take a sample, and for now, you can do other kind of compounds, but we'll talk mainly about hydrocarbons, that is, carbons that contain carbon, hydrogen, and maybe oxygen. So you weigh the sample out, the compound you're analyzing, you weigh some of it out so you know how much it weighs. Put it into this furnace here. And this furnace has an inlet for oxygen gas. So a lot of oxygen is flowing through, so you get complete combustion. There's no air in here, just oxygen, because air has nitrogen in it and other things, and you would get other products. We don't want that. So we just put pure oxygen through here, and flush it out, make sure there's just oxygen. And then we have some traps. We have a water trap, and we have a carbon dioxide trap. So as the product combusts, the compound combusts, it's made into a gas. The products are gases, carbon dioxide and water gas. Those are the two, by the way, for hydrocarbon, the only two products would be carbon dioxide and water. And when it's hot, they're going to be gases. So anyway, the oxygen gas pushes the carbon dioxide and the water gas through here. All the water is absorbed here. All the carbon dioxide is absorbed here. Anything else that's present just gets flushed out the end. Now, what we do is we weigh this. This comes off and this comes off. We weigh this before the experiment and after the experiment, and the same thing over here. And the difference in mass after the experiment and before the experiment is how much water was produced. And the same thing for the carbon dioxide. So what we know at that point is the mass of carbon dioxide that came from this compound and the mass of the water that came from this compound. Now see, the idea is that all of the carbon in this compound goes into making carbon dioxide, and that's the only place that carbon dioxide came from. So we know that however much carbon we have here, that's how much carbon we had here, moles and grams. Also, for hydrogen, the only place hydrogen came from is the sample, and the only place it went and all of it from the sample went here. So we know that however much hydrogen we have here is how much hydrogen there was initially in the sample. Now we can't do the same thing for oxygen because we're pushing oxygen through here. So if some of the oxygen here and here came from this, and it might have come from the sample too. But I'll show you how to deal with that in just a second. So here's how we do it. This is a step-by-step procedure for you to use whenever you're doing a combustion analysis problem. So we use this example. We weigh out our sample. It's a hydrocarbon. That means it has carbon, hydrogen, and maybe oxygen in there. This many grams of it, and after the experiment, we reweigh the traps, and it ends up that we had produced this many grams of carbon dioxide and this many grams of water. What's the empirical formula of the compound? This is what we do. First thing you do is you convert the grams of carbon dioxide and water to moles, and then get moles of carbon and moles of hydrogen. So divide the mass of carbon dioxide by its molar mass, got moles of carbon dioxide. And because in one carbon dioxide there's one carbon, it's a 1-to-1 mole ratio, which you can see from the formula. That's just the same number of moles of carbon. Same thing for water. Find moles of water and moles of hydrogen. So we take the grams of water, divide by the moles of water, and that gives us moles of H2O. But there are 2 moles of hydrogen in 1 mole of water, so we have to multiply that by 2 to get our moles of hydrogen. Now we have to deal with oxygen. So what we do is use the law of conservation of mass. We know that the mass of the original compound must equal the mass of carbon plus hydrogen plus oxygen. So what we do is we first convert the moles of carbon and hydrogen back to grams, give them this many grams of carbon, this many grams of hydrogen, and then we subtract them from the mass of the original sample. Now, if this number is close to 0 after we do the subtraction, that means there was no oxygen in the original sample. But in our case, yeah, there's like 2.791 grams of a difference, which means it had to come from oxygen. So now we know grams of oxygen. We're going to convert this to moles of oxygen by dividing by the molar mass. All right, so now we have moles of all the elements in the compound, carbon, hydrogen, and oxygen. Now we just do like we did with empirical formula. This is the empirical formula calculation. We divide by the moles of the element that we have the least of. In our example, the least number of moles was oxygen, 0.1744. So we divide moles of carbon and moles of hydrogen by moles of oxygen, and we get 6.5 or so moles of carbon for every 1 mole of oxygen and about 9 moles of hydrogen for every 1 mole of oxygen. Now, remember the rule is at this point we look at these numbers, and if they're closer than 0.1 to a whole number, we get to just round to the whole number. But this isn't, which means we have to multiply by something over itself. Do you know what we're going to multiply by? Yeah, 2. 2 over 2, right? And here's the thing. If we multiply one ratio by that number over itself, we have to do everything in that compound. So we have to do this too. So it's going to look like this. .5 moles of carbon per 1 mole of oxygen times 2 over 2 gives us 13 moles of carbon per 2 moles of oxygen. And down here we get 18 moles of hydrogen per 2 moles of oxygen. And so now we know our empirical formula is C13H18O2. Here we go.